Next, let's talk about magnetic poles. Every magnet has at least two poles. Though you can have magnets with three poles, north, south, north, or south, north, south, or even more sometimes. Um, you can have magnetic fields without poles. That would be like a magnetic field surrounding a current carrying wire. But for permanent magnets, they always have poles, and any loop of wire also has poles. The north pole of one magnet always attracts to the south pole of another magnet. So this is similar that positive and negative charges attract, north and south poles attract. The magnetic field is strongest near the poles of the magnet, but even stronger inside the magnet. Now, for permanent magnets, it's difficult to get inside the magnet, but with a coil, it's easy to get inside the magnet, as we'll see.
I've got like about 1,000 little magnets here instead of like 20 little magnets. This is just pieces of staples. That's all this is. And you will see them all line up like little compi, but this will help us get a better understanding of what the field looks like. They are all lining up with the magnetic field. Okay. And you can see it kind of works that you can see where the field is strongest. Where they're all bunched up together, that's where the field is strongest. What parts of this magnet, this permanent magnet, is the field strongest at? At the poles. Notice it's pretty weak right here and it's weak right there, but it gets stronger as you get close to the poles.
The magnetic field is actually strongest inside the magnet, but we can't get inside there. Note that every single magnetic field line makes a complete loop. If you follow any line, it will go all the way around and then meet its own end, forming a complete loop. Also note that just like electric field lines, where the field is strongest, the lines are closest together, and you can see them, that they're close together inside the magnet, but outside the magnet, they're also close together by the poles. Now, if a magnet is allowed to spin freely in the Earth's magnetic field, for example, a compass is pivoted on a pin so it can spin however it wants. If it's allowed to spin freely, the north pole of the magnet will generally point to where Santa Claus and the polar bears live. That's up here. And the south pole of the magnet will generally point towards Florida and Antarctica, where the penguins live. That's why they named the magnetic poles north and south, because one side of the magnet always pointed to where Santa Claus was. They called it the North Pole. One side of the magnet always pointed towards where the penguins are, the Antarctica or South Pole. So they called the two ends of a magnet the North and South Poles. But you got to be careful here, because please note that the North geographic pole, I'll capitalize it to distinguish it, the North geographic pole, where Santa lives, I've marked that right here with this red thing, is actually near the South magnetic pole. And the South magnetic pole is actually in Canada. This red dot is where Santa lives. It's where the polar bears hang out. Notice that is actually near the South magnetic pole of the Earth. That's why the North Pole of a compass attracts it, because it's near the South magnetic pole. Although near the equator of the Earth, the magnetic field is approximately parallel to the surface, way up here in the northern hemisphere, there's a significant component of the magnetic field which is perpendicular to the surface, which can be observed using this compass that's free to spin in 3 dimensions. This map right here shows how the direction of the magnetic field at the Earth's surface does not actually point in the direction of the true geographic north, and it's off by more depending on where you are. So this red line right here indicates the direction towards geographic north. In other words, if you follow this red line all the way to where it ends at the top, you will hit the axis of the Earth's daily rotation, the geographic North Pole where Santa Claus lives. These blue lines, by contrast, represent the direction of the Earth's magnetic field. In other words, towards the south magnetic pole of the Earth is the way that these arrows are pointing. And that is the south magnetic pole, which is near the north geographic pole. And you'll notice in Michigan, according to this map anyway, the direction of the magnetic field is about 5 degrees west of where the actual North Pole geographically is. So the magnetic field doesn't point exactly towards the geographic pole. In fact, the magnetic field of the Earth changes and changes so rapidly, this map's already out of date. Right now, the magnetic field in Michigan is about 6 degrees off of geographic north. And you can see that the farther away from this line that you go, farther away from this line, the people in Wisconsin there have it lucky because their compasses actually point to geographic north. Way over here in Washington, over on this side, their compasses point 20 degrees east of geographic north. Another important point is that every permanent magnet has both north and south poles. Both of them. If you break a bar magnet, you get 2 smaller magnets. So here's a bar magnet right over here. And if I broke that in half, what I would end up with is 2 magnets for sure, but it'll be different in that each magnet will have a south pole and a north pole. The south pole, notice it stays the same when you break it. On this side, you'll have a north pole right where it was before, but you'll also have a south pole right there. So every permanent magnet has both north and south poles. Sometimes you can get a north, a south, and a north that looks something like this. Or you can get, north, south, north. That's like kind of 2 magnets that have been stuck together. Or you can get south, north, south as well. But if you break a magnet, you get 2 smaller magnets, each with minimally a north and a south pole. No magnetic monopoles have ever been found. Scientists are searching for them. A magnetic monopole would be something like this. A magnet that has only a north pole. And if this were true, the magnetic field lines would go out of it just like they go out of a positive, like electric field lines leave a positive charge. This has never been found. We do not yet see that those exist at all. Now, if they did exist, it would be really nice because then our equations would be a whole lot neater. But so far, at least in this part of the universe, we have never found them. So much so that we've created a law called Gauss's law in magnetism that says there are no magnetic monopoles. As soon as you find one, though, you win the Nobel Prize, and we get to change Maxwell's equations so they're just a lot nicer. So, no magnetic monopoles found yet, although people are desperately searching for them because it seems like they should exist, but we can't find them.